Gentlemen, today we are going to talk about Fraunhofer diffraction. Now, what's Fraunhofer diffraction? There are two types of diffraction we talk about. First, we have to make sure we have the word diffraction squared away in our heads. Diffraction is light bending around obstructions. And when light bends around obstructions, you're going to have interference like we talked about in class yesterday and like we're going to study in lab today. So things will make a lot more sense after lab today than they do right now. But
I have a question about that.
What's that?
The lab we're doing today is from last week or it's different?
No, it's the one on wave optics.
Different lab.
Different from last week, yes.
So the one we were supposed to do last week, you just skipped it.
That's correct. So when the light bends around obstructions, it turns out that if you want to do a careful calculation of what's going on, you have to do what's called Fresnel. That's guy's last name. Diffraction calculations. Fresnel diffraction is what we usually call near field diffraction. It's where you have to take into account that you could have angles that aren't small. Fraunhofer diffraction is in the far field where we can make approximations to make life much simpler. So we're only going to look at Fraunhofer diffraction here. If you look at the integrals for Fresnel diffraction, they're very interesting. You have the Cornu spiral or something, and it's kind of interesting, but it's also kind of difficult. So setting up a diffraction problem. Let's suppose that I have a diffraction grating like this. When you wore these in class yesterday, what did you observe? Pretty colors. Where were those pretty colors coming from? The lights. And those pretty colors were separated, I said, because of the lines in there. And we call that separation of the colors diffraction. Now, diffraction is bending around a color or bending around objects, so that's kind of a specialized diffraction. I do have to be careful here. I always forget that this is putting out 2,450 volts. Right, you don't want to just play around with that. Although it's only 6 milliamps. So there is the pattern we get when we shine the laser beam through the glasses you were wearing yesterday.
That means it's purely red?
It's what?
It's just red light?
Yes, 632.8 nanometers. So what you see there is very distinct dots, right? And you see a grid of them because this has gratings that are both horizontal and vertical. If I rotate the grid, the positions of the dots rotate with it. So it's called a grating because it has lots and lots of slits. I'll show you an example in lab today with just 2 slits, and you'll see the 2 slits is not nearly as exciting looking. The multiple slits makes it clearer. Now that's the children's toy version. Here is 530 per millimeter. Not quite what we'll be using in lab, but close. So 530, what's different? Besides the reflection there. Okay, the center dot is more bright. What about the ones on the sides?
Can you see them?
Yeah, you can.
Oh, they're way over there.
They're farther out. Okay, so having the lines, this has the lines close together, it makes those farther apart. And so what we want to do today is to understand what in the world is going on making that happen. So I'm going to plug this and get to it. So here's the setting of our geometry. We have coherent. Do I have the word coherent somewhere? I guess I don't. We have coherent light coming in and hitting these slits. So each little hole there between the gray is the obstruction. And then the hole between it, of course, is the slit. And so light goes through those slits And the light that goes through those slits, of course, if we're correct, if, let's not say were, let's say if Christian Huygens was correct, then the light that goes through each one of those little slits is going to behave like a point source. So what direction is the light going to go from a point source? All directions. So we should have light going out in all directions from each one of those little slits. The picture doesn't show light going in all directions because it's only showing the rays that are going to contribute to positive or constructive interference. We'll have rays that go everywhere. So taking just this top slit, I could draw rays from this top slit that are going like this and like this and like this and like this. You know, all those rays exist, but the picture is only showing those that are going to give you constructive interference. So because you saw that you only have certain points where we had bright light. We call those points with the bright light the maxima. The central one is the 0th order, and that's the first order on each side, the second order going out to the second one, and so on. So that's our geometry. Well, we want to understand how this works and be able to get an equation for it. Something that's important is right here. The intensity, change to a thicker pen now. Intensity is proportional to the electric field magnitude squared. That's going to be important for our understanding of what we get there. What is intensity? Do you remember what intensity means?
Energy transfer.
Energy per
meter. Second.
It's the energy per area per second. So it's the power per area.
Yeah, each of those components. Just have to put them together and square one.
Pretty close. So the power per area is proportional to the electric field squared. So the electromagnetic wave is oscillating electric fields. We're going to deal with the electric field in our calculation. I said it's also oscillating electric fields. It's obviously oscillating electric and magnetic fields. We could do it with magnetic fields or with electric fields. It's just by convention that we do it with the electric field. So we're going to work with the electric fields to try to calculate why we have this constructive interference. Now here is the part that makes this Fraunhofer diffraction. For Fraunhofer diffraction, we have a screen that's very far away compared to the separation between the slits. And in that case, the difference in the path length, actually I say between the separation slits, between the most separated of the slits we're using in diffraction grading. The difference in path length can be easily calculated because with the small angle approximation, essentially every single one of these rays in the picture, all of these rays are parallel, essentially, for the small angle approximation. This picture does not at all look like those rays are parallel, does it? This picture would be applicable for the Fresnel diffraction calculation because it illustrates what really happens. But if you're far enough away, those rays are so close to parallel that we'll just treat them as parallel. And so what's the difference in path length? Well, all we do is we take a line and we go like this. This line is supposed to be perpendicular to each one of these. And of course, in this picture, it does not at all look perpendicular to each one of those. But it's perpendicular to all of them because of the far field approximation. And thus we can just use geometry and say, this is the difference in length between my first one and that one. And of course, this one here and so on. And then I can just use, well, if these are right angles, then this side here is the hypotenuse. This side here is the path length difference. And I can simply say that the path length difference, delta L, is equal to this hypotenuse that we'll call a capital D, sine theta. So the difference in length for each one of these rays that gets there is going to depend on what that D is and what the angle is between there and there. That's what this picture here is illustrating, theta. Now it used lowercase d here to be the smallest separation. And so the distance between the smallest ones, as shown in that little, okay, I'm erasing everything here. That little blow up is just showing this here and using the lowercase d for this separation. And then, yeah, that's totally a right angle. This here is the delta L, the difference in path length. And that's the angle theta. So that's, you can see why there's a difference in the Fraunhofer and the Fresnel pictures. This picture is to make it fit on a page and not look stupid, it's got to look near range, not far range. So I have a picture that is the best version we can make of far range coming up. Well, it's coming up in a few slides, so I won't jump to it. So now let's do our calculation. Once again, we're going to start with coherent light. The light will all be in phase when it hits our slits. So the light, when it hits the slit, is going to have electric field magnitude is equal to E0, that's just the intensity, having to do with the intensity of light, sine of omega t plus some phase angle phi. Let's make life easy and set that phase angle to 0. Why complicate things by carrying on a phase angle when it's arbitrary? So we're just going to say this is the intensity of light when it gets to the slit, or not the intensity, excuse me, the electric field of light when it gets to the slits. In time, it's going up and down, up and down, up and down. Now, when it goes from the slit to the screen, it's going to take time to go from the slit to the screen. And because of the time it takes to go from the slit to the screen, you're going to be at a different phase when you get to the screen than it was when it got to the slit. That's pretty obvious. But if you have a different path length, it's going to take a different time to get to the screen, so you're going to be in a different phase when it gets to the screen. So the light that was completely in phase when it hits the slits is not going to be completely in phase when you get to a specific point on the screen, because you had different path lengths from each slit to the screen. So what we're going to do is say, well, if I just take two slits, so I'm going to take two adjacent slits, then the path length difference is going to be very telling to me. It's going to tell me about how different they're going to be in phase. So this bottom line is saying, just for the original, light going from, let's say, the top slit has a distance L to the screen, and so the time difference is L over C, right, because it's going the speed of light, so time is distance over speed. And so plugging that into our equation, we have the electric field at the screen is E0 sine of omega t plus 2 pi L over lambda. Now we're going to have the top of the screen and the two different paths, so we're going to now say, well, we're going to have L1 and L2. L1, the path from one slit, L2, the path from another slit. And so I add up the intensity that I'm going to get, or the electric field I'm going to get, going through those two slits at one point on the screen. And so L1 and L2 are the lengths from one slit to the screen, one to the other. And then we have to use a trig identity. Trig identity is actually, let's just not put the A there. Sine of A plus sine of B equals 2 sine of, now I got to make sure I get these right. Nope. Yeah, 2 sine of A plus B cosine of A minus B. So using that relationship, that identity, we take the electric field from the two slits is equal to the electric field from one slit, E0, times 2 because it's 2 slits. Well, times 2. I mean, that's how it works out. And then we have sine of adding the 2. So we have omega t plus pi L2 plus 1 over, or L2 plus L1 over lambda. This here fluctuates in time. And then we have a part that's a constant here. That's going to tell us how the intensity varies. Right? The one that's fluctuating in time, it's going to be going maximum electric field 0, minimum 0, maximum. It's not going to tell us about how the intensity varies. It's just going to go from -1 to 1 back and forth. But that second one is going to give us a variation in the electric field strength depending on where I am on the screen, and thus in the intensity depending on where I am on the screen. So what's going to be important here is L2 minus L1. L2 minus L1 is the difference in path length. That's the delta L, and we've already worked out. Come on. Is d sine theta. And so plugging that in, well, you see there I have it written down what I just wrote. So I'm going to have, okay, I'm going to do it over here before I get to the answer there because, so here's my total electric field. So intensity over the intensity 0 is going to be the electric field over electric field 0. The electric field 0 would just be the electric field of 2 slits. So it'd be 2E0. So I'm going to put 2E0 there because we had 2 slits. And then we have to do the square of that. So that's going to be equal, well, 2 squared, it turns out, is very simple. 4. E0 squared is on bottom. On top, I have this whole thing we did here. So I'd have 4E0 squared sine squared of omega t plus pi L1 plus L2 over lambda cosine squared of pi come on. So that's the ratio of my intensity. But this is the intensity at a specific time. We generally look at the average. So this would be intensity is equal to, notice these things here just canceled. So that's the intensity at any time. Well, if we look at the average intensity is going to be, what's the average of sine squared? What's the average of sine squared over an integer number of periods? Sine squared is symmetric between 0 and 1. So the average is 1/2. So I average is equal to I ought times 1/2 times cosine squared pi over lambda L2 minus L1. So that's the average intensity. Why this 1/2? Well, the average intensity initially would have been 1/2 of the peak intensity initially. So it's the average intensity I would have had with just going through 2 slits, or the light going through 2 slits, times this term here. Now, the last thing I have to do is substitute in for L2 minus L1. So I'm going to put IOT average instead of putting the 1/2. I put the average for the IOT. And then I have cosine squared of pi over lambda. And then going up here, where was it? It was right here. D sine theta is what I have for and so there's the equation that gives me the intensity fluctuations from what I've done technically is just a double slit because I only did the calculation for 2 slits. So I should have that equation. Right here, I dropped off the averages, but it should have had average. The intensity average is intensity 0 average cosine squared of that. Now, questions. At what argument is cosine squared going to be a maximum? What angle makes cosine squared a maximum? Okay, 0, pi, 2 pi, 3 pi, 4 pi, etc., as well as the negative. And so if I have that thing that's the argument of cosine squared is an integer multiple of pi, then I'm going to have a maximum. So I have, it's a lot easier to do it that way than to take the derivative stuff, right? Maxima when pi over lambda d sine theta is equal to m pi. Where m is any integer. Any integer, including 0. Well, we can quickly cancel the pi's. And we have the equation that we're going to use in the lab today. D sine theta is equal to lambda. So that's where you get the equation for the maxima for a 2-slit diffraction grating. What about minima? Once again, if we look at that cosine squared, what angles give you a minimum for cosine squared? Pi over 2, 3 pi over 2, 5 pi over 2, etc. And so I'm going to have a minimum when that argument, pi over lambda d sine theta, is equal to m plus 1/2 pi, where again, m is any integer, positive or negative. And we are smart enough now that we will cancel those and get d sine theta is equal to m plus 1/2 lambda. So that's our equation for minima. I'll put a box around the second form here, maybe. And yeah, works for me. So we're able to find where the maxima and minima were for a double slit. Not very hard, right? Did it involve calculus? No, we didn't do any calculus. We didn't have to take a derivative because we know the cosine function so well. If we didn't know the cosine function so well, we would have used calculus to find the maxima and minima. So that's for a double slit. But my initial picture wasn't a double slit. My initial picture was mini slits. What's the difference in a double slit and mini slits? By the way, now I can get down. Here's the picture that shows an accurate Fraunhofer depiction. It's showing these as parallel rays, and then we have the compressed scale so that we can fit it in one picture. What's the difference in single slit and multiple slits?
Single slits. You have two diffractions, one from each from one side of the slit, and then multiple slits. You always have it. Oh wait, I don't know.
Well, we are learning. We're in class, not. In other words, you're not supposed to necessarily know what you're talking about when you're taking class. You're learning. So here's the key difference. If I have two slits, only two slits, if I move ever so slightly away from the peak, what's happened to the phase difference between the light rays from the two slits? If I just move a really small amount. Are they perfectly in phase anymore? Are they exactly out of phase? No. So what are they closer to? In phase or out of phase? They're closer to in phase, which means that cosine squared term is still going to be pretty close to 1. So if I move just a little bit away, it's only going to drop in intensity by a small amount. Now, if I had 3 slits, the phase difference between these two would be very different, or very small. The phase difference between these two would be very small. But they would be different phase differences. And so I would have more destructive interference because of the difference in the phase differences. And so if I have a lot of slits, so if I have like 100 slits that are all contributing to the light at that point, I'm going to have the phase differences pretty much randomly spread out. And so I'm going to have just as much that are constructive as destructive, and on average, it'll add up to 0. So if we have lots of slits, what happens is only the places where we had peaks are we going to have the peak. Only the maxima have light. Everywhere else is destructive. And so the multiple slits makes the destructive interference regions large and the constructive small. Because you have to have exactly the right situation for constructive if it's multiple slits. With 2 slits, if they're a little bit out of phase, it's still mostly constructive. So that's why our diffraction gratings are not just double slit, but lots of slits that are very close together, so we can have lots of light adding together so that if it's not exactly in phase, it's adding up to 0. So these here, these are 530 grooves per millimeter. My beam has a diameter of about 530 millimeters. So that means I have light from about 530 different slits all adding up together at one location, which is why everywhere it looks pretty much destructive except for right at the maximum. Picture looks really good when you blow it up this much. Okay, that was our first part. And let's go on to part 2. Superposition from a single slit. Now, I warn you, the single slit is much more complicated than the double slit or the multiple slit. Why? Because now we're going to have a continuous range of phase differences. Continuous range of phase differences means, are we ever going to have constructive interference? Well, we're going to have some places where it's closer to constructive than others. And so what we're going to do is calculate how this works. And notice we have the phasor concept. We use the phasors when we talked about electricity, the phase vectors. So we're going to use phase vectors again now for the electromagnetic wave. We're going to have the phase of the wave, the phase indicating when you have peak for your wave. And so we take our single slit and say, well, what if this was a whole bunch of tiny slits? Let's make it an infinite number of infinitesimal slits and do it like it's a whole bunch of separate slits. So we start by saying that E sub n is the electric field that comes through one of the slits. So if E0 is the electric field that would go through the entire slit, then the electric field that goes through one of our infinitesimal slits is going to be the total electric field E0 divided by capital N, the total number approaching infinity of slits. And then we have sine omega t plus 2 pi path length difference. L sub n now is the path length difference between the bottom or the top of the slit, whichever you want to use. And wherever I am in the slit, I'll divide by lambda. So that's using exactly the same equation that we just worked out for the electric field that we get with the path length that we used for the single slit. But then we do some substitution. Now, I did not make this diagram. It used different variables, so you can see that I rewrote in hand using the same variables that I'm using. So this used for the phase difference from the top of the slit to the bottom of the slit. This diagram had used phi, which stands for phase. My work used beta because I was trying to be consistent with our textbook. Actually, this is the first year I've used this textbook. I didn't check to make sure I'm still consistent with this textbook. What nomenclature does it use in this textbook? Do you guys check? We should check that, but I'm not going to check it right now. I'll check it after class. I should have just taken the pictures from your textbook. That would have made it so it was consistent. Okay, so coming back to this, the path length for the nth slit, lowercase nth slit is, we have capital N approaching infinity slits. The lowercase nth slit is the distance of lowercase n capital N, that fraction of the total slit height, away. And so the path length difference is going to be the path length from the path length for the nth slit is the path length for the top plus the fraction of the way we are down times the entire slit width A. That tells us how far we are. And then sine of the angle of viewing. So that's what I have right here. That's the path length from the lowercase nth slit from the edge, where L0 is the path length from the edge of the slit. But then using the fact that this has 2 pi times the path length over lambda, I substituted that in. So right here I have the substitution. And then I just rearranged. So in magenta, I have separated out 2 pi over lambda a sine theta, which is the maximum phase difference between the top and bottom of the slit. So we now have an equation that says the electric field for the nth slit, lowercase nth slit, is this right here. So all we have to do is add all of those together. Well, if these are continuous slits, what do you have to do to add together a continuous function? You have to integrate. So we're going to do an integral now. So there's calculus. But we're going to do calculus in a way that you've probably never done it. We're going to do it geometrically. We have to know the idea of calculus is adding each one of them up and adding them up continuously. Now this diagram here shows a bunch of black arrows. That would be the discrete addition. That would be adding up this slit plus this slit plus this slit plus this slit. Each slit has the same magnitude, the E0 divided by capital N. Excuse me. And so each of those arrows is the same length, but they have a different direction, a different phase angle. And so you have, each one has a different phase angle. Now those phase angles change linearly as you move across the slit because it was just proportional to lowercase n, which slit you're on. So now if we go to integration, adding up the continuous, instead of having individual vectors, we're going to have just a perfect circular arc. And so for doing our integral, we are going to simply add up the length of the arc. So here is the diagram that shows the whole 9 yards. I mean, this diagram is solving the problem, but when you look at it, you don't know that it's solving the problem. It doesn't seem right that that's solving the problem. So let's look at this diagram, make sure we understand what it is. The bottom, I will change the color to blue in my best tracing. The blue E sub 0, that's the total electric field strength that you have at the opening, at the slit. It's the total electric field that goes through the slit. So that's going to be our reference for intensity. Take that, square it, and that's proportional to the original intensity. The red straight line, the one that's marked E with the subscript theta 0, that is the difference between the starting and ending point when you add up vectors. Remember, adding vectors, the resultant is going from the starting point to the ending point. And so that arc is showing the adding of vectors, and the solution for adding the vectors is the straight line connection. So the E theta 0 is what the electric field strength is when I add them all together. And so I can immediately say intensity over intensity 0 is equal to E theta 0 over E 0 squared. So I have to just calculate what those two things are geometrically. Now there's some more to the geometry here. So what more is there to the geometry? Well, beta was the maximum difference in phase angle from the top of the slit to the bottom of the slit. And so that means this entire angle here was beta. And from geometry, it's very easy to establish that since that's a perpendicular angle and that's a perpendicular angle, this angle right here is also beta. Why is that important? Well, it's not going to be important to the way I'm doing this, but it's something shown here. I've solved this probably 10 times, 10 different ways, and many of the ways it was important. The way I did this morning, it was trivial. The way I did it, I need to always do it the way I did this morning. So how do I get the length of an arc in a circle? Let's say I have a circle of radius 1 meter. How do I find the length of an arc of angle theta?
Isn't it half the angle of the central? No. So we use secant. No.
You're thinking a lot harder than it really is.
We use the angle.
Yes, we use the angle. The arc length is just the radius times the angle. Well, what's the angle? If it's beta for that angle, then it's just going to be r times beta. That's really simple. The other part's not quite as simple, but it's not hard. I have a right triangle here. It has a hypotenuse of r and an opposite side that's half of E theta 0. So I can say that sine of beta over 2 is equal to E theta 0 over r. Right, that wasn't very hard either, which means that E theta 0 is equal to r sine of beta over 2. Works for me. Whoops, I forgot one thing. I totally forgot one thing. This was 1/2 of E0. 1/2 of E0 because E0 is going all the way across, and that was only half of it. So I have to throw the 2 there. I was very concerned suddenly that it wasn't going to work out. I made a mistake. So using this E theta 0 and this E0, I can come over here, and that's equal to 2. I'm going to have to move some stuff to give myself space. when you get too close to the edge. I blame everything on Microsoft. They don't deal with things properly. So my ratio of intensities is just that. Now that seems simple except for what was beta. Beta wasn't something simple. Beta had to do with our angle theta. So now I need to put my angle theta into this. And so I have and so beta is written right there, 2 pi over lambda a sine theta. And it was beta over 2, so let's just divide out that 2. So that's the equation for my intensities. So now we look at this and we say, aha, when are we going to have peak intensities here? What argument for sine theta gives me a maximum?
Pi. No, not pi. Pi over 2.
Yes. So when the argument, which is pi over lambda a sine theta, is equal to m plus 1/2 pi. That's what he said. He said pi over 2. And because it's squared, pi over 2 or 3 pi over 2, which is minus 1, will both be maxima. So those would be our conditions for maxima, right? It's not perfectly right because the bottom's also changing. So that's approximately right. If the bottom was constant, it would be correct. And so that would give us, so this is approximate. And so we cancel the pi's and we have a sine theta is equal to m plus 1/2 lambda. That's approximately correct, but not exactly correct. What about the minima? Okay, 0 or integer multiple of that. Well, that one is exact because the 0 doesn't matter what you divide it by, except it does matter in one case. 0 divided by what is not 0?
Oh, 0.
If you divide by 0. So what we're going to find here, once again, just canceling the pi, whoops, that's not the pi. Canceling the pi's, we have a sine theta equals m lambda, but that includes when m is 0. We have to check when m is 0. It's indeterminate. So how do you check if it's indeterminate? Use L'Hopital's rule.
Wait, L'Hopital's rule. Oh, it works on any.
Yeah.
Okay.
So we're going to have to use L'Hopital's rule here. So what we're going to do And I'm going to go to make my calculation much simpler. I'm going to go back to I over I0 is equal to sine of beta over 2 divided by beta over 2 squared. And so I'm going to say let me use alpha here for my new angle. That's my function. So I don't have to worry about any chain rule action. I can just say, let's take the derivative of the top, divide the derivative of the bottom. So what's the derivative of sine squared theta, or sine squared alpha? Okay. And what's the derivative of alpha squared? 2 alpha. Now, as alpha approaches 0, that's going to be I can actually use the small angle approximation and stop here. I can use the small angle approximation that's a small angle approximation. So that means this is equal to 2 alpha cosine alpha over 2 alpha equals 1. So our intensity approaches 1. It approaches the peak intensity at the 0 point. So that means that if we go back here, oops, too far. If we go back to this, these were minima except m equals 0 is a maxima. Now, because class time is over, we won't find the true value for the maxima. The true value for the maxima, you have to take the derivative, set the derivative equal to 0. And so we actually have taken the derivative here, and so we would have to take this and set it equal to 0 and then solve for the alpha. We're halfway there, but we don't have time to finish it.